Sleep and study. Don't forget to subscribe.
The system we're considering in this lecture is the quantum harmonic oscillator. There are a few ways to solve the Schrodinger equation for the quantum harmonic oscillator, but what we're going to do in this lecture is a solution more or less by pure cleverness. The solution is called the solution by ladder operators, and we'll see what that means in a few minutes. Just to set the stage, the potential that we're working with here is the potential of a harmonic oscillator. The amount of energy, essentially, that you get if you displace a particle attached to a spring from equilibrium. If you remember spring potential energy, the potential as a function of x is 1/2 the spring constant times the displacement x squared. But it's traditional to write this instead in terms of the angular frequency. The angular frequency of the oscillations that result when a mass m is on a spring with spring constant k is the square root of the spring constant divided by the mass of the particle. And if you substitute this in here and mess around with the simplification a little bit, you end up with 1/2 m omega squared x squared. So this is the form of the potential that we'll be using. What this looks like, if I plot it, is a parabola. Not the world's prettiest parabola, but you get the idea. And we know a little bit about what solutions to the Schrodinger equation should look like under circumstances like this. Let me draw this a little lower so I have room. If I have some energy E in this combined energy wave function axis, making a diagram of what the wave function looks like, if I start my wave function here, you know in this region, the energy is above the potential, so the Schrodinger equation solutions have to curve downwards. And what they end up looking like is, well, something like this, say. Now, in the regions outside here, where the potential is above the energy, the Schrodinger equation solutions curve upwards. And in the case of the harmonic oscillator solutions, they curve just down to kiss the axis. And you end up with a nice sort of hump-shaped wave function. If you have a higher energy, say up here, it's entirely possible to get solutions that look different. Suppose I started my wave function here, pointed at some angle. The energy now is higher relative to the potential, so the wave function is going to curve more, and it's possible to make it curve down to the point where when it reaches this point now where the potential is higher than the energy and it starts curving back upward, you again get a wave function that just smoothly joins in with the axis, giving you a sort of nice normalizable wave function. So these are the sorts of solutions that we expect to get. If you want to get these solutions just by, like drawing them, like I just did, you can conceptually understand what they look like, but quantitatively you'll have to do a lot of fine-tuning to get these energy levels exactly right and to get the initial conditions here. I just started my wave function. How high up should I start my wave function? Or in this case, should I start it at the middle? Should I displace it? What should this angle here be? Fine-tuning like that is hard, and we'll see how to do that in the next lecture. But in this case, we're going to make a solution by cleverness instead of fine-tuning. To set that up, let's go back to the time-independent Schrodinger equation. This is the general time-independent Schrodinger equation, where now we're going to be substituting in the harmonic oscillator potential, 1/2 m omega squared x squared. That means the harmonic oscillator time-independent Schrodinger equation that we actually have to work with minus h bar squared over 2m times partial derivative of psi with respect to x squared plus 1/2 m omega squared x squared psi is equal to E psi. So this here is the Hamiltonian operator. The time-independent Schrodinger equation is also often just written as h psi equals E psi, and that's fine. Let's take a closer look at this Hamiltonian operator. Maybe we can do something with it. The cleverness comes in this step. Consider factoring the Hamiltonian. Well, I can simplify this a little bit by pulling out, for instance, a 2m here, and writing this as the momentum operator squared. This is essentially p squared over 2m, the kinetic energy part. This is the potential energy part. If I pull out 1 over 2m, what I get, 1 over 2m p hat squared plus m omega x quantity squared. This is suggestive. If we had numbers, and I had something like a squared plus b squared, I could factor that over the complex numbers as ia plus b times minus ia plus b. If you expand this out, you'll end up getting a plus a squared from multiplying these, a plus b from multiplying these, and similar to the cross terms in, say, a minus b times a plus b, the cross terms end up canceling out, and we would end up with what we started. Now, this is suggestive. You can't actually factor operators like this because they're not numbers, they're operators, and operators don't necessarily behave the same way numbers behave. We'll see what that means in a minute, but for now, let's just suggest looking at things like this. Plus or minus I times the momentum operator plus m omega x, where x now is the position operator. Now x, the position operator, just entails multiplying by x, so perhaps I should put a hat here, perhaps I shouldn't. Doesn't really matter. This is what we're considering now. I haven't justified this in any way beyond saying it kind of looks like maybe it would factor. Well, does it factor? These things are called ladder operators, and they're traditionally defined, just to make the notation a little bit simpler, a hat, and there's either a plus or a minus on this. Let me draw this a little bigger. A hat, plus or minus in the subscript, and these are defined to be 1 over the square root of 2 h bar m omega. The constant just makes things more nice overall, times a minus or plus I p hat plus m omega x. This is now the position operator x hat. So this is the traditional definition. Let's see. If we have something that properly factors, what we should have is that a hat minus times a hat plus is our Hamiltonian. Is this true? This is an operator algebra problem, and operator algebra problems are tricky to do without test functions, but initially we can just write this out. We have two a's being multiplied together, so we're going to have a 1 over 2 h bar m omega out front, and then we're going to have I p hat plus m omega x times minus I p hat plus m omega x. Once again, hats on the x's if you prefer. So far, we've just written down our operators in order. Now, if I actually try to expand these out, 1 over 2 h bar m omega. Now, this term, I times minus I, that's just plus 1. So we would get p hat squared. So far, so good. For this term, this is okay as well, plus m squared, omega squared, x hat squared. That's still okay. We're still on track. This was more or less what our Hamiltonian looked like. The cross terms get a little more interesting, though. We have a term like this, which gives us, let's see, we're going to end up with a minus I from this, minus I m omega, and we have x hat, p hat. We're going to end up with something very similar from this term. We're going to have an I, we're going to have an m, we're going to have an omega, except in this case we're going to have p hat, x hat, not x hat, p hat, as we had here. So I'm going to factor the constants out and do that in the right color. That means we're going to have minus p hat, x hat here. So this is what we get when we expand this out. This part here looks a lot like the Hamiltonian. So we're on the right track. It's actually like 1 over h bar omega times the Hamiltonian. This part, though, this is a little more difficult to work with. And it turns out that this piece right here, this sort of thing appears a lot in quantum mechanics, and we have a name for it and a notation for it. And the notation is x hat comma p hat in square brackets. This is called a commutator. And fundamentally, the fact that I can't just subtract these two things from each other and get 0 is one of the most fundamental parts of quantum mechanics, one of the most fundamental features of quantum mechanics. So, let's talk about commutators in a little more detail. The commutator in general is defined for two operators A and B to be what you just saw on the last page. First, I have A, B, and then I subtract the opposite order, B, A. So if I acted on this, or if I used this operator, this combined operator, to act on a wave function, I would first let A act and then let B act. And I would subtract that from what I get if I let B act and then A act. Just to make that a little more explicit, if I had A, B minus B, A acting on some wave function, I would say that's A, B, psi minus B, A, psi. You don't necessarily get the same answer for both of these things because the order in which operators act is important. So let's look then at our commutator. The commutator we had in the last slide was x and p. Commutator of x and p is x hat, p hat minus p hat, x hat. And let's allow this to act on some wave function psi. In order to make my notation correct, I ought to have the same sort of psi here. So if I allow this to act on psi, first we're going to have x hat, p hat, psi minus p hat, x hat, psi. And what this means is x hat is acting on p hat acting on psi. And this is p hat acting on x hat acting on psi. We have definitions for these things. X hat is just x multiplied by something. And p hat is minus I h bar times the derivative of something, in this case, psi. Our second term here is minus I h bar times the derivative of, with respect to x, of x times psi. When I apply the derivative here, I have to use the product rule since I have a product of these terms. I'll have to hit x in one term and psi in the other term. So, on the leftmost term here is easy to deal with, though. It's just minus I h bar x d psi dx. Actually, let's factor out a minus h bar, I h bar, from both terms, since they both have it. So x d psi dx is my first term here. Then I have minus, if I use the derivative on the x, derivative of x with respect to x is just 1. So all I'll be left with is the psi remaining untouched in the product rule. And if I let the derivative hit the psi, I'll leave the x untouched, and I'll have the derivative of psi with respect to x. This is good because here I have an x d psi dx minus x d psi dx. So I can let these terms subtract out and cancel. And what I'm left with, I have a minus I h bar times minus psi, which is just going to be I h bar psi. So I started with the commutator acting on the wave function, and I just got constant multiplied by the wave function. So I can drop my hypothetical wave function now and just write an equation involving the operators again. The commutator of x and p is I h bar. It's a weird-looking equation, but you can see, if you recall from the last slide, what we're going to end up with. when we evaluated a minus hat, a plus hat, we ended up with 1 over h bar omega times the Hamiltonian, plus some constants. And if you flip back a slide, the I h bars end up actually canceling out, and we just end up with plus a half for our constant. So while we did not succeed in fully factoring the Hamiltonian, we did get the Hamiltonian back, plus a constant. And if you reverse the order and repeat the algebra, a hat plus a hat minus, you end up with the same sort of thing. It looks very similar. You get 1 over h bar omega times the Hamiltonian minus a half instead. What this means is we can express the Hamiltonian in terms of these ladder operators and these constants. What we get for the Hamiltonian, h hat, is h bar omega times a minus a plus operators minus a half. Or alternatively, the Hamiltonian is equal to h bar omega a plus a minus plus a half. So these are the sorts of things that we got from our operator algebra after attempting to factor the Hamiltonian. That was pretty clever, but it didn't actually get us a solution. It just got us a different expression of the problem. The cleverness really comes in considering ladder operators and energy. The time-independent Schrödinger equation here is h hat psi equals E psi. So suppose we have some solution psi to the Schrödinger equation. We can then express the Hamiltonian in terms of these ladder operators, h bar omega times a plus a minus operators plus 1/2 acting on the wave function should be equal to E times the wave function. The clever part is this. What if I consider h hat times a plus psi? What happens to the wave function if I allow a plus to act on it before I allow the Hamiltonian to act on it? Now, assuming this is the case, maybe we can manipulate our expressions here involving the Hamiltonian and the ladder operators to get something with which we can apply our solution. Let's see what happens. Expressing the Hamiltonian now as ladder operators, h bar omega, a hat plus, a hat minus, plus 1/2, now acting on a plus hat psi. Forgot my hat there, sorry. Looking at this, you can take a plus psi and distribute it in to the expression in parentheses here. H bar omega, a plus hat, a minus hat, a plus hat psi, plus 1/2 psi. Put another way, I'm really just distributing the operator in. And that's actually a more convenient way to look at it. So I'm going to erase my psi's here, and I'm going to leave my psi outside the expression. Oops, and I forgot an a plus hat here. Sorry about that. Just distributing the a plus in here, you'll end up with plus minus plus, and just plus on the 1/2. Now, you notice I have an a plus here, and an a plus here. If you think about factoring this out to the left, that's actually allowed as well. I can rewrite this as h bar omega, a plus hat in front of the expression a minus hat, a plus hat, plus 1/2, all acting on psi. That's okay. What's nice about this is if you look, we have here now an h bar omega and an a minus a plus. If I had the appropriate constant here, which would turn out to be minus 1/2, I would have the Hamiltonian back. And getting the Hamiltonian back means we might be able to apply our Schrödinger equation. So let's rewrite this as h bar omega, a plus hat, times a minus a plus, minus 1/2 plus 1. I haven't changed anything now, except this piece. This is my Hamiltonian. I had two expressions for the Hamiltonian that I got from calculating the product of ladder operators. One if I did A plus first and then A minus, one if I did A minus first and then A plus, and they were different by the sign that appeared here. So the fact that this is the Hamiltonian allows me to rewrite things a little bit. Turns out I can rewrite this whole expression as A plus hat acting on the Hamiltonian, and you have to distribute the h bar omega in, Hamiltonian operator plus h bar omega acting on psi. So I'm starting to lose my ladder operators, which is a good sign because I don't actually want expressions with lots of ladder operators in them. I'd like expressions with things that I know in them. And it turns out you know what happens when the Hamiltonian acts on psi. So if I distribute psi in here, I'll just have psi times h bar omega and the Hamiltonian acting on psi. But you know the Hamiltonian acting on psi is E times psi. So we're definitely making progress now. This is going to become A plus hat times E plus h bar omega psi. This now is all constant. So it doesn't matter if I put it in between the ladder operator and the wave function or not. So I can pull that out and make this E plus h bar omega times ladder operator A plus acting on the wave function psi. If I rewrite my entire equation then, I end up with h hat acting on ladder operator psi, A plus psi, is equal to E plus h bar omega ladder operator acting on psi, A plus acting on psi. This looks a lot like the Schrödinger equation for a wave function given by A plus psi. So, if psi is a solution to the time-independent Schrödinger equation, A plus psi is also a solution to the time-independent Schrödinger equation with this new energy. That's really the clever part. If psi is a solution, A plus psi is also a solution. That's really quite interesting. What that means is if I have one solution psi, I can apply the ladder operator, which I've just been writing as A plus hat here, but we know what the ladder operator A plus is. It's a combination of the momentum operator and multiplication by x with appropriate constants thrown in. We know about A plus psi. If we knew the wave function, we could actually do this. It would involve taking some derivatives and multiplying by some constants. We can do that. So this gives us some machinery for constructing solutions from other existing solutions. We haven't actually solved the system yet. There's a little bit of cleverness left. And this has to do with ladder operators and the ground state. What we showed on the last slide was that if psi was a solution, then A plus hat psi was a solution with energy E plus h bar omega. It turns out A minus hat psi, you can follow through the same algebra, is also a solution, but it has energy E minus h bar omega. So suppose we have some solution, psi, and I'll call it psi sub n now. If we apply the ladder operator, A plus psi, we'll end up with some wave function psi n plus 1. It's another solution to the Schrödinger equation. It has a slightly higher energy. The energy has been increased by the amount h bar omega here. I can repeat that process, and I'll get, say, something I would call psi n plus 2. And you can keep applying the ladder operator over and over and over, and you'll generate an infinite number of solutions with higher and higher and higher energies. We can also apply the ladder operator A minus hat, and you'll get something I'll call psi sub n minus 1 with slightly lower energy. The energy has been lowered by an amount h bar omega. You can apply the ladder operator A minus hat as many times as you want, of course, as well, and you'll get psi sub n minus 2, or psi sub n minus 3, or psi sub n minus 4, or psi sub n minus 5. Every time you apply the lowering operator, the ladder operator A minus hat, you get another solution with lower and lower and lower energy. But we know if we have a wave function with very, very low energy, it's going to behave very strangely. If your potential, for instance, is your harmonic oscillator potential, it looks like this, and your energy, E, is below your potential V of x, then if I start my wave function, say, anywhere, really, let's start it here. The fact that the energy is below the potential for the entire domain of the potential means that over the entire domain of the wave function is going to be curving away from the axis. The wave function is going to be blowing up. That's a problem. I cannot have solutions with arbitrarily low energy. What that means, cannot have solutions with very low energy. What that means is that if I apply this lowering operator over and over and over again, sooner or later, I have to get something that I can no longer apply the lowering operator to. Something will no longer give me a meaningful solution. And it turns out the best way of thinking about that is there is some wave function such that A minus acting on that wave function is equal to 0. If we have a state like this, this will be our lowest energy state, and I'll call it psi sub 0. This is a necessary condition for getting a normalizable wave function. If we did not have this condition, we'd be able to keep applying the lowering operator, and we would sooner or later get solutions that were not allowed. That's a problem. So let's figure out what this actually implies. We know what the lowering operator is. We know what 0 is. We ought to be able to solve this. This is going to be an ordinary differential equation just given by the definition of the ladder operator. 1 over 2m h bar omega in the square root times the momentum operator h bar d by dx plus m omega x acting on psi sub 0 is equal to 0. This we can solve. This is a relatively easy ordinary differential equation to solve, in fact, because it's actually separable. If you mess around with the constants, you can convert this into the differential equation d psi dx is equal to minus m omega over h bar x psi. And these are now psi zeros, sorry. This can be directly integrated. I can rewrite this as d psi over psi is equal to minus m omega over h bar x dx. And if I do this integral, integrating both sides of this equation, what you end up with, after you simplify, is that psi sub 0 is equal to e to the minus m omega over 2 h bar x squared. E to the minus x squared for our ground state, for our lowest energy psi sub 0, for our lowest energy solution. There's a normalization constant here, and I'll save you the trouble of calculating the normalization constant out. It's m omega over pi h bar to the 1/4 power. So this is our ground state. Now it's off to the races. By consideration of the Hamiltonian and attempting to factor it and defining ladder operators and exploring the consequences of these ladder operators, in particular that we ended up with any single solution giving us an infinite number of solutions by repeatedly applying A plus and A minus, the necessity of a normalizable wave function, the necessity of having a lowest energy state, meant that we got an equation that was simple enough that we could solve it with just simple ordinary differential equations. Now, there's really no such thing as a simple ordinary differential equation, but this was a lot easier to solve than some ordinary differential equations. What that ended up giving us in the end was psi 0, our lowest energy state. We can then apply the raising operator, A plus, over and over and over again to construct an infinite number of states. To summarize, Here's a slide with all of the definitions. The raising and lowering operators, the ladder operators, A plus and A minus, the expressions that you get from simplifying the Hamiltonian in terms of the ladder operators. I want to highlight these two expressions because I have not completely derived them. I have argued that the ladder operator A plus applied to some wave function psi sub n gives you psi sub n plus 1, but I haven't told you anything about the normalization. You could apply this operator over and over again and renormalize all of the wave functions you get as a result, but it turns out there's a pattern to them, and that pattern is that what you get by applying the ladder operator A plus to psi n is not psi n plus 1, but psi n plus 1 times this square root of n plus 1. Likewise for the lowering operator. There's a nice explanation in the textbook of how you can use still more cleverness to derive what these normalization multiplicative factors are. Our ground state we got from applying the lowering operator to some hypothetical wave function, which when we solve it, we ended up with this, our psi sub 0, our lowest energy wave function. Putting all of this together, you can come up with an expression for the nth wave function, psi sub n, in terms of psi sub 0. You have to apply A plus n times. This superscript n here means to apply A plus n times. For instance, A plus hat cubed would be A plus, A plus, A plus, all acting on, say, if there's a psi in here, all acting on the psi, just one after the other. And if you calculate the energies that we get, applying the Hamiltonian to our lowest energy wave function, and then knowing that the raising the operator A plus gives you a new solution with an energy that's increased by the amount h bar omega, you end up with the energies. So we actually know everything about the solutions now. We know the lowest energy solution, we have a procedure for calculating higher energy solutions, and we know the energies of all of these solutions. So that's wonderfully good. To give an example of how these things are actually used, let's calculate psi 1. We know psi 1, buying black a little easier to read, psi 1 is going to be equal to A plus acting on psi 0, and there's that normalization constant, the square root of n plus 1, except in this case n is 0, so this is just going to be 1. If I substitute in the definition of the operator A plus, that's 1 over that square root of 2 h bar m omega minus I p hat plus m omega x, where p hat now is minus I h bar d by dx. This is my raising operator. That's all acting on psi sub 0, and we know psi sub 0, given in normalized form, m omega over pi h bar to the 1/4 power e to the minus m omega over 2 h bar x squared. We just have to evaluate this, taking derivatives of this exponential and multiplying it by x. So let's continue with that. Moving our normalization constant out front, m omega over pi h bar to the 1/4 power over this square root factor, 2 h bar m omega. Simplifying this expression out, we end up with minus h bar d by dx plus m omega x, all acting on e to the minus m omega over 2 h bar x squared. Now, this term with the m omega x, that's going to be easy. The derivative here is going to be relatively straightforward as well. What we end up with is the constants we had out front, and taking the derivative of an exponential, we're just going to get the exponential back. So we're going to have an h bar e to the minus m omega over 2 h bar x squared times the inner derivative, the derivative of what's in the exponent itself, which is minus 2 x, let me actually write this out, minus m omega over 2 h bar times 2x. That's okay. The minus sign here and the minus sign I had out front will end up canceling out. I can simplify, I can cancel out my 2's, I can cancel out an h bar. That's all I'm going to do with that term for now. The other term is easy. M omega x e to the minus m omega over 2 h bar x squared. So that's our result. We have an e to the m minus m omega, etc., over x squared in both of these terms. So I'm going to pull that out to the right. And if I pull my constants out to the left, I have an m omega and an m omega in both of these terms, so I can factor that out. But what you end up with at the end, after all is said and done, the only step I'm skipping now is to simplify the constants. What you end up with is m omega over pi h bar to the 1/4 power. There's not much we can do about that. Square root of 2 m omega over h bar x e to the minus m omega over 2 h bar x squared. Both of these terms had x and x in them. So these terms just add up, and this is what we end up with at the end. This is your expression for psi 1. The algebra here gets a little bit complicated, but fundamentally what we're doing is calculus, taking derivatives, multiplying, manipulating functions, applying the chain rule, and turning the crank, more or less. The formula we started with here does give us machinery that we can use to calculate any wave function that we might want as a solution to the time-independent Schrödinger equation for the quantum harmonic oscillator. To check your understanding, here is an operator algebra problem. Given that x hat is the position operator and t hat is the kinetic energy operator, essentially p squared over 2m, calculate the commutator of x and t. That's just defined as this. The one tip I have for you here is to be sure to include a test function when you expand out these terms. And when you take second derivatives, do it as a sequence of 2 steps. Don't just try and take the second derivative twice in one step. You may have to apply the product rule. We've heard about the solution to the harmonic oscillator time-independent Schrödinger equation by cleverness with ladder operators. This is the differential equation we have to work with is something that can be solved by other techniques. In particular, it can be solved by power series. Power series is a common solution technique for ordinary differential equations, so it's useful to see how it applies to the time-independent Schrödinger equation. The equation we have to solve is this. Essentially, H operator psi equals E psi, where we're now only talking about psi as a function of x. We have a second partial derivative with respect to x that comes from the kinetic energy part of the Hamiltonian operator, and we have a potential energy part here, where the potential function we're now working with, v of x, is the potential in a harmonic oscillator, 1/2 m omega squared x squared, basically proportional to the square of the displacement of a particle from some equilibrium position. Often, the first step in solving an ordinary differential equation like this is to make some change of variables to simplify the structure of the equation. Basically, what we're looking to do is get rid of some of these constants. And it turns out the change of variables that we want to use here, and you can determine this with a little bit of trial and error, knowing how change of variables works, is we want to, instead of x, we want to use x is the square root of h bar over m omega times some new coordinate c. Now, what happens when we substitute in new coordinates here? Well, we have to worry about psi of x here, and here, and here. Psi is going to have to, in some sense, change a little bit in order to be represented as a function of c instead of x. We also very clearly have an x here, and we have to worry about the second partial derivative with respect to x. So let's work through this step by step, and you'll see how these substitutions can be made. First of all, we can pretty easily handle these psi as a function of x because we know what x is. X is the square root of h bar over m omega times c. So we'll have minus h bar squared over 2m. Don't have to worry about the constants. Second derivative of psi, now square root of h bar over m omega c is the argument for psi, but we're still second differentiating with respect to x. dx squared, pardon me, plus 1/2 m omega squared. Now, substituting in for x, this is relatively easy. We're going to get this squared, h bar, over m omega c squared, times psi, and the argument of psi is again going to be this root h bar over m omega c, equals e times psi, where again the argument of psi is this function of xi. You can see there's going to be some cancellation here. I can get rid of some m's and some omegas, but I'll leave that until later. The only difficult term to deal with here is the second partial derivative with respect to x of psi, which is now a function of xi. Now, when you're taking the derivative of something with respect to a function of something else, you have to use the product rule. Sorry, not the product rule, the chain rule. So I'm going to apply the chain rule to this derivative term, and I'm going to split it up into two steps, two first derivatives instead of one second derivative, just to see how each of those steps applies. So first of all, minus h bar squared over 2m times the derivative with respect to x of the derivative with respect to x of psi of xi. Now, I can take the derivative of psi with respect to xi. That I know how to do. That's just d psi d xi, because psi is a function of xi. But in order to turn this into a partial derivative with respect to x, I have to multiply by the derivative of xi with respect to x. So this is the chain rule at work here. And I know how to take the derivative of xi with respect to x, because I know xi is a function of x. This is just going to give me square root of m omega over h bar. What I get if I solve for xi and then just differentiate with respect to x. This can then be pulled out front. It's a constant, doesn't contribute anything. Minus h bar, oops, don't want to be an orange. Minus h bar squared over 2m times our constant, root m omega over h bar, times partial derivative again with respect to x. But now I'm taking the partial derivative of psi with respect to xi. So again, I have to apply the chain rule. What I'm going to get differentiating psi with respect to xi is a second derivative of psi with respect to xi now, times again a partial derivative of xi with respect to x. You can do this all in one step if you know that the partial derivative of xi with respect to x is simple. If the partial derivative of xi with respect to x had some problems in it, some dependence, you would have two separate functions here. You wouldn't be able to factor it out as a constant, and you'd have to apply the product rule to this term. So be careful when you're doing this. Don't just assume that you can take a second partial derivative with the chain rule in one step. But the second step here, again, partial derivative of xi with respect to x gives me the square root of m omega over h bar, which as a constant I can pull out front and combine. What I'm left with for this term then is minus h bar squared over 2m times m omega over h bar, again giving me some nice cancellations, times the second derivative of psi with respect to xi. So this converts my derivative with respect to x into a derivative with respect to xi. I've converted my x into xi, and all of my other x's into x's just by changing the arguments of psi. So the overall equation I get now, minus h bar squared over 2m, m omega over h bar, second partial of psi with respect to xi, plus 1/2 m omega squared h bar over m omega, xi squared psi, equals e psi. This is good because we can do some cancellations. We can, for instance, cancel one of the omegas here, and we can cancel the m. We can also cancel an m here and one of the h bars. What's nice about this is I have h bar omega over 2 here and h bar omega over 2 here. So I have the same constant, and I'm going to move both of these constants, factor them out, and move them over with the e to lump all of my constants together. I'm also going to change the ordering of the terms to get my two psi's together and mess with the signs a little bit. But the final equation you get is the second derivative of psi with respect to xi is equal to xi squared minus some constant k psi, where k is what we got when we aggregated all these constants together. It's need an equal sign there. K is equal to 2e over h bar omega. So this is a differential equation that's substantially simpler than the differential equation we had here. Just by rearranging constants, we haven't actually changed the structure of the solution any. This differential equation isn't something that we want to just go ahead and try and solve with power series, though, and you'll see why in a moment. Solutions that are most easily represented by power series are solutions that are only interesting near the origin. And this equation tends to be difficult to represent with power series because of what happens for large values of Xi. So let's look for something called an asymptotic solution. Let's look for a solution for large Xi. Xi much, much greater than 1. What happens when Xi is much, much greater than 1? Well, if Xi is much, much greater than 1, I don't care about K here. It's going to be about equal to Xi squared. Xi squared minus K is about Xi squared. That means the actual differential equation we have to solve is second derivative of psi with respect to Xi is Xi squared psi. Oh, and I've unintentionally changed notation here. This is a derivative of psi, not a partial derivative of psi. That doesn't really matter. The partial derivative and the total derivative are the same because psi now is only a function of x. Likewise, I should also probably write capital psi here instead of lowercase psi. That's just an error. Apologies. This approximate equation has solutions. In the case of an asymptotic solution, we don't really care about the exact solution. An approximate solution is good enough if we can still use this approximation in our solution. So our approximate solution, and you can check this, is that the wave function is approximately equal to a times e to the minus Xi squared over 2 plus b e to the Xi squared over 2. Rewrite that, or make it more look like a C. So this equation is an approximate solution to this equation. And you can see that by taking the second partial derivative of psi. I'll just look at this term, for instance. The second partial derivative of this term, d squared dx, or d Xi squared of e to the minus Xi squared over 2 is, and you can plug this into whatever computational algebra tool you want, Xi squared minus 2 times e to the minus Xi squared over 2. So this, again, approximately for large values of Xi, is going to be about equal to Xi squared. So second derivative of this effectively pulled down a Xi squared and gave us our function back. And that's what our approximate differential equation is. Now, if you had a minus sign in front of the Xi and the exponent here, you'd end up with much the same sort of expression. So you can see this is effectively an approximate solution to our approximate differential equation. This is useful in a couple of ways. First of all, there will be large values of Xi. Unlike the case of the infinite square well, there's no sound reason for believing that the wave function will go to 0 for large values of Xi. It's certainly not required by the laws of physics. It is, however, required by the laws of mathematics. In order to have a normalizable wave function, this asymptotic behavior can't have any of this in it. So if we want our wave function to be normalizable, then b must equal 0. That's a requirement. What that tells us then, if we have something that's going to be a solution to the time-independent Schrödinger equation, its asymptotic behavior will be given by this. So psi is approximately equal for large Xi to some constant e to the minus Xi squared over 2. That's an approximate solution. This goes to 0, which is good, for large values of Xi. This term behaves itself, but terms that go to 0 for large Xi are hard to represent with power series, since power series are fundamentally polynomials, and if you have, say, a large value of Xi raised to a large power, it's unlikely to go to 0. So what we'd like to do is effectively remove this asymptotic behavior from our differential equation. Going back to our exact differential equation, once again, this should be a capital C, a capital psi. we want to remove that dependence. And we can do that by writing our psi as psi now being a function of xi equal to some other function of xi multiplied by e to the minus xi squared over 2. If we substitute this equation in, hopefully we will be able to derive a new differential equation for our new function h that no longer has this asymptotic behavior, essentially factoring it out. So in order to substitute this in, we're going to need a second derivative of psi with respect to xi. So let's go ahead and calculate that. The first derivative of psi with respect to xi is, well, we have a product now. We're taking the derivative of a product. We have to use the product rule. So first, the derivative will hit the product, dh dxi. Apologies for my messiness here. Dxi. Leaving the second term unchanged, e to the minus xi squared over 2, plus the derivative hitting this, we'll leave h of xi unchanged. I'm not going to write h of c, just leave it as h. And then the derivative of this term. And the derivative of this effectively brings down the derivative of the exponent, which is going to be a minus xi. So I won't have a plus sign here. I'll have a minus sign. I'll have a xi. And I'll have an e to the minus xi squared over 2. These are what we get from the product rule here. Differentiating the exponential gave you the exponential itself multiplied by the inner derivative minus xi. So that's our first derivative. Our second derivative necessarily gets a little more complicated, taking the derivative of the first derivative. With this term, again, we have a product. So first, the derivative hits this, and we end up with the second derivative of h with respect to xi times the exponential unchanged, e to the minus xi squared over 2, plus what we get from leaving this term unchanged and taking the derivative of this. And we know what that looks like. That's sort of what we got here. Except the derivative is going to be what's unchanged. We're going to have a minus dh dxi xi e to the minus xi squared over 2. That's what we get from our first term. And if we continue taking derivatives, we need to differentiate the second term. We have a product now of 3 terms, so we'll get 3 additional terms here, but we already know what one of those terms looks like. If the derivative hits the h, we'll get a first derivative of h and a xi and an e to the minus xi squared over 2 left untouched, which is coming in with a minus sign. And that's exactly what we've got here. So I'm just going to make a little space here and say minus 2 times this term. The other 2 terms, when the derivative hits the xi here, it's just going to eliminate the xi, and we're going to be left with h e to the minus xi squared over 2. And when the derivative hits this term, we're going to bring down effectively another minus xi. So we're going to have plus h xi squared e to the minus xi squared over 2. Now, what's nice about this is we have an e to the minus xi squared, e to the minus xi squared, e to the minus xi squared, e to the minus xi squared. We can factor that out of all the terms. And, well, let me just write down what we get. The second derivative here now is equal to d squared h dxi squared minus 2 xi h. Sorry. Changing the order of the terms, minus 2 xi dh dxi plus rearranging c squared minus 1 h with an e to the minus xi squared over 2 factored out. This is all our left-hand side of our equation. And comparing our left-hand side and our right-hand side from up here, this psi now being h times e to the minus xi squared over 2, both the left-hand side and the right-hand side here are going to have this e to the minus xi squared over 2, which means we can cancel it out. So we've effectively gotten rid of our exponential dependence. Also looking at the left-hand side of the equation, you notice this xi squared h, e to the minus xi squared. If you look at the right-hand side, we have a xi squared times h e to the minus xi squared over 2 from the psi. So on the left-hand side and the right-hand side, we have this xi squared term. and these actually end up canceling each other out. So what I'm left with, in the end, the final differential equation, after rearranging some terms, is d squared h dc squared minus 2c dh dc plus, rearranging constants, you end up with a k minus 1 h. And that's it. This is all just equal to 0. So this is our transformed ordinary differential equation. This is what we want to solve with power series. So how do we solve this? This doesn't really look all that more simple than the equations we started with. Solution by power series essentially proceeds as a guess. What we guess is that our solution, in this case our solution is h of xi, is going to be given by power series with unknown coefficients, a0 plus a1 xi plus a2 xi squared plus a3 xi to the third power. You get the idea. This sum continues, potentially infinitely, so let's write it as an infinite sum. Sum of j equals 0 to infinity of a sub j xi to the j. This is our general solution, and if we knew all of these coefficients, we would know everything about our solution. In order to substitute this into our differential equation, we're going to need to know first derivatives and second derivatives of this power series. So let's calculate a first derivative, dh dxi. You can look at these terms individually and tell easily what the derivatives are. The derivative of a constant is 0, so this term doesn't appear. The derivative of a1 xi is just going to be a1. The derivative of a2 xi squared is going to be 2a2 xi. 3, this is going to give us a 3a3 xi squared, etc., just taking the derivative of polynomials one term at a time. We can express that in this summation as well. Sum from j equals 0 to infinity of taking the derivative of each of these terms effectively brings down the j and subtracts 1 from the exponent. So you'd have j, a sub j, xi to the j minus 1. And you can tell just by plugging in j equals 0, j equals 1, j equals 2 that this is what you're going to get. For instance, if I plug in j equals 0, I have 0 times a0. So whatever these things are, it's 0. If I plug in 1, I have 1 times a1 times xi to the 1 minus 1, or xi to the 0, which is just a constant. So I just have a1, etc. You can continue this process to take the second derivative. Once again, either term by term, giving me 2a2 plus 3 times 2 times a3 xi plus, etc. Or you can do it in the summation. Sum from j equals 0 to infinity of, again bringing down the exponent here, j times j minus 1 times a sub j times xi to the j minus 2. And once again, you can plug in j equals 0, j equals 1, j equals 2, etc. if you want to check to make sure that it works. So, into our differential equation, we are going to have to substitute these things, these sums. Our differential equation was d squared h dxi squared minus 2xi dh dxi plus capital K minus 1 h. And that was all equal to 0. So, easy terms first, this is going to be substituted in for h. The power series for the derivative of h is going to be substituted in for the derivative. And the power series for the second derivative is going to be substituted in for the second derivative. Where we're going with this is we'd like to get an equation that doesn't have any x's in it. And what that means is that we'd like each of these sums to have xi raised to the same power so that we can factor out the summation and have just the coefficient and the xi all by itself, nice and simple. In order to do that, we need to make the power that xi is raised to in each of these terms in the sum the same. For instance, I have this summation for h. It has a xi raised to the j power. And I have this summation for the second derivative of h. it has a c raised to the j minus 2 power. So what I'd like to do is rearrange the indices in this sum so that I have a c raised to the j power. This is just a redefinition of index. I'm not actually going to change anything about this equation, but I'm going to rewrite it as a sum over j going up to infinity of every time I see a j, I'm going to write a j plus 2 so that I have c to the j for my power. So this j will become a j plus 2. This j minus 1 will become a j plus 1. This a sub j will become a sub j plus 2. And, running out of space, c to the j, multiplied out. Now, this is a little more subtle because this is outside the sum. I can't just replace 0 by 2 here. I actually have to replace it by minus 2. But if you look at what happens for minus 2 and minus 1, those terms end up contributing nothing. So I'm going to start my sum at 0 anyway. This has the advantage of making the summation itself look like the summation I've got here, which makes things easier to factor out. The term for the first derivative of h is a little more subtle, but it actually ends up being easier to handle because it appears in the differential equation multiplied by c. If I imagine multiplying this infinite sum by c, I can distribute the c through all the terms, and it's effectively going to just add 1 to the exponent of all the x's. So I'm already going to have a c sub j here. So if I write out all these sums together, for the second derivative, I had a summation over j going up to infinity of j plus 2, j plus 1, a to the j plus 2, c to the j, minus 2, and I'll distribute the c into the sum for the first derivative now. 2 times the sum, again it's a sum over j going up to infinity, and the inside of the sum here was j, a sub j, c to the j, after I multiply through by c. My final term here has a k plus 1, or k minus 1, sorry, out front, and has a sum over j going up to infinity of just a sub j, c to the j. And this is all equal to 0. Now, each of these terms has a sum over j and a c to the j power in it. What that means is I can effectively treat these sums lining up terms that are raised to the same power of c by effectively just pulling out the sum. So I can write this whole thing as a sum over j going up to infinity of j plus 2, j plus 1, a to the j plus 2, and if I'm factoring the sum out on the left, I can factor the c to the j out as well. So I'll write the c to the j out here on the right. If I factored out the c to the j, I'm now done with the first term. I can move on to the second term, which has a 2, a j, and an a sub j. Factoring c to the j out, I'm done with that term. And my third term just contributes a k plus 1, a sub j. And that's it. This is all multiplied by c raised to the j power, and it's all equal to 0. So this is what I get if I substitute in the power series solution for h in this differential equation. The nice part about the way I've manipulated the sums now is that the c to the j has been factored out. So this number in these square brackets represents the coefficient that is multiplied by c to the j power in my power series. So in order for this equation to hold for all values of c, we actually need this term here in square brackets to be equal to 0. Hopefully that's not too surprising. Essentially, this means our polynomial here, there are relationships between the terms in our polynomial, in our power series. And that, reproducing, that's the condition. This is the condition we got from the coefficient of all the terms in the power series in the last equation had to equal 0. This has to hold for each term in that infinite sum separately. And this is the key step in a power series solution to an ordinary differential equation. We started with an ordinary differential equation that had strange asymptotic behavior and some funny constants. We factored those out. Then we substituted in a power series, which turned out to be a reasonably effective guess, because we were able to separate the equation out into a series of relationships. Effectively, this is an infinite number of equations now. Instead of one equation involving an infinite sum, we have an infinite number of equations, each involving only a few terms. This is called a recurrence relation because it tells you what these coefficients are in terms of each other. We have a to the j plus 2 and a to the j. A to the j, a sub j. So we can simplify this equation a little bit and solve for a sub j plus 2. And it's equal to these things. I'll mess with the signs a little bit, moving things around. 2j minus k plus 1 over j plus 2, j plus 1, a sub j. So this tells us what our a sub j plus 2 is in terms of a sub j. So if you remember our original expression for h of c, it was a0 plus a1 c plus a2 c squared plus a3 c to the third plus a4 c to the fourth, etc. If I told you what a0 was, you would be able to use this expression, substituting in 0 for j. You could tell me what a sub 2 was. So a sub 0 determines a sub 2. A sub 2, in turn, using j equals 2 in this equation, you could tell me what a sub 2 plus 2, a sub 4 is. So a sub 0 determines a2, determines a4, determines a6 in an infinitely long chain. The same holds for the odds. If I told you what a1 is, you could substitute j equals 1 in this and find a sub 3. If you knew a sub 3, you could find a sub 5. You knew a sub 5, you could find a sub 7. So we effectively have these two chains of coefficients. If you know a0 and a1, you can find all of your coefficients in your power series solution to this ordinary differential equation. We have these two unknowns, a sub 0 and a sub 1, and those correspond to the two unknowns you have when solving any other second-order ordinary differential equation. For instance, Newton's law, the second-order ordinary differential equation that governs the motion of bodies, has initial conditions. The position and the velocity of the particle must be known in order to determine the specific solution to the ordinary differential equation that you are working with. Those position and velocity numbers are analogous to a0 and a1 under these circumstances. We have two free parameters in both cases. Now we have a power series here, and if I tell you a0 and a1, you potentially have infinitely many terms determined by a0 and a1. Does that work? In particular, if you have an infinitely long power series, you may be worried about issues of convergence. Does the power series converge? Does it give you a sensible solution, or does this infinite sum blow up? Those are valid concerns. Really, what the question is does this power series terminate? If the power series terminates, you don't need to worry about convergence. However, if the power series does not converge, or does not terminate, converge is the wrong word, does not terminate, you can, by appropriately waving your hands, show that the power series you get, now looking back at the recurrence relation and proposing that j is extraordinarily large, we're dealing with very high order terms in the power series, you can show that the resulting power series for those large order terms behaves like e to the c squared. This is a problem, because our wave function psi was defined to be h times e to the minus c squared over 2. If h now is e to the c squared, what we'll end up with is e to the c squared over 2. Those large order terms in the power series will behave like e to the c squared over 2. And if our power series doesn't terminate, we will have a lot of these terms. So if our wave function is going to behave like c squared over 2, that was a problem. We used the requirement for having a normalizable solution to eliminate terms like this from our original solution. We had an approximate asymptotic solution that looked like this that we ruled out because it was non-normalizable. So it's appeared again as a result of our power series. That's not going to give us a good solution. What that means, therefore, our power series must terminate. It must end. And what that means is that we have some highest power. How could we get a highest power? Well, go back to our recurrence relation. Suppose our highest power is n. Our recurrence relation for n tells us 2n plus 1 minus k over n plus 2, n plus 1, multiplied by a sub n, is a sub n plus 2. If we know that n is a highest power, we know this must equal 0. We can't possibly have an a sub n plus 2 if our highest power is n. So if we're going to have a highest power, we know this must equal 0. A sub n is non-zero, then this must be 0. And in order for this to be equal to 0, we have a condition on numerator here, namely that k is equal to 2n plus 1. Now, if you remember what k was related to the energy. This is ultimately where quantization comes from in the power series. But before I talk about quantization, I want to make another note about the structure of the power series. Our power series looked like A0 plus A1 c plus A2 c squared, etc. If my highest power were, say, A2, if I was going to terminate here, that's fine. I can have a non-zero A0, that determines a non-zero A2, and then my recurrence relation gives me 0 for A4, effectively terminating my sum. That's okay. But if I have a non-zero A1, the recurrence relation for A1 will not give me 0 for A3. And I won't get 0 for A3, I won't get 0 for A5 or A7 or A9 either. And I'll still have an infinite sum with my odds. Effectively, what this means is that if I want a normalizable solution, not only does my power series have to terminate, but if I'm going to say terminate at an even power, I have to have no odd powers. I have to use 0 for A1. So that takes away a good deal of the freedom I had when I was choosing my solutions. If I'm going to have a solution with even powers in it, terminating on an even power, I have to have no odd powers in my solution at all. So either we have evens or we have odds, not both. So there's some limits on our power series that we get from this requirement of normalization. We have a condition here on k, and we have a condition on, depending on where we want to determine our power series, what other terms we're allowed to have. So, as I mentioned, this is what gives us quantization. We had k was equal to 2n plus 1. What k gave us, k was originally defined to be 2e over h bar omega. And if you combine these relations together, you end up with a condition on E, the separation constant, which we know is related to the energy. It's equal to h bar omega times n plus a half. This is our quantization condition, which we get from the requirement that our power series terminate. If our power series, what this means is that we have to choose our energy very carefully. We have an integer for n, and we have only a specific discrete set of allowed energies will give us normalizable solutions. What this looks like in the context of the solutions to the Schrödinger equation is if we have our solution, say, written as a function of xi, treating this as now a sort of combined energy wave function axis. If I have, say, the energy of the wave function here, the energy constant, E, if my wave function, say, starts here, and the energy is too high, you know that the wave function has a concavity that curves downwards when the energy is above, sorry, not curves downwards, curves towards the axis when the energy is above the potential. So we're going to be curving towards the axis here. We curve towards the axis until we reach a point where the potential is higher than the energy, at which point we start curving away from the axis. But if our energy is too high, we won't curve away from the axis enough to smoothly join with our axis. And then once the wave function has crossed the axis, it curves away from the axis, away from the axis, away from the axis, and blows up. It gives us a non-normalizable solution. This is what we were talking about in the context of if the energy was not exactly right, we got this sort of e to the x squared behavior, x squared over 2 behavior for large values of xi. If the energy is slightly too small, you get the same sort of behavior. The wave function doesn't curve towards the axis enough, so then when it starts curving away from the axis, it misses the axis entirely and curves upwards. Curving downwards, curving upwards, oops, blows up. There is a happy medium in the middle, and that wave function curves downwards and then starts curving upwards at exactly the right rate to join with the axis. I'm not doing a very good job drawing this. This plot is duplicated in your textbook if you want to see what it looks like properly. But the amount of upwards curvature you get for the proper value of the energy results in the wave function downwards and then curving upwards and just barely joining in with the axis, never to leave. And you just have this e to the minus x squared asymptotic behavior for our overall solution. So, what do these things look like? Well, the first few solutions we get, we know they're going to be power series, and they're going to have terms like A0 plus A1 xi plus A2 xi squared, etc. But the first ones are pretty simple. A0 plus A1 xi plus A2 xi squared plus, etc., going on to infinity. If I'm asking you for H0, the power series that terminates at A0. In order to get that, I have to say A0 is not equal to 0 because I want to have a solution with even powers in it, 0 being the only even power. I have to set n, the highest power I get, equal to 0. I correspondingly have to set A1 equal to 0, and I have the freedom to do that. What you get is pretty boring as a polynomial. H0 is just A0. Not particularly useful. The wave function I get as a result, though, is useful because this is the lowest energy state. Psi sub 0 as a function of xi is A0 times our e to the minus xi squared over 2 function. So this is our ground state. This is our lowest energy stationary state solution to the time-independent Schrödinger equation for the quantum harmonic oscillator. If I want to know what the second solution is, this one is going to terminate at A1. So I'm going to have A0 equal to 0 because I don't want any even powers in my solution. I'm going to have to use n equals 1 for my highest power, and I'm going to have A1 not equal to 0 or I won't have a solution at all. H1 then is just going to be A1 xi, and that gives me a wave function psi1 of xi is A1 xi e to the minus xi squared over 2. That's my first excited state, the second energy level in the quantum harmonic oscillator. Stationary states, at least. If I want to know something slightly less trivial, I want to know what happens when I terminate my series at A2. If I terminate my series at A2, I'm going to have A0 not equal to 0 because I want terms with even powers in them. I'm going to have to use n equals 2 to terminate my series in my recurrence relation. N now determining the energy, determining what the how the recurrence relation terminates things. And I'm going to have A1 equal to 0 again, because I don't want any odd powers. In order to figure out what this looks like, we're going to have to go back to the recurrence relation. And if I write the recurrence relation for known energy given by this condition that we got to require the series to terminate, what the recurrence relation looks like actually has this number n, the highest power in it, instead. And it looks like minus, I don't need a parentheses just yet, minus 2 n minus j over j plus 2, j plus 1, all multiplied by a sub j. So this is what you get if you substitute the correct value of the energy into the recurrence relation. If I use this, h2 of xi is going to be a0, which is something non-zero, plus, what do we get for a sub 2? Well, we have 0 substituting in for j, and 2 substituting in for n. So I'm going to have minus 2 and a 2 minus 0, and then in the denominator here, I'm going to have 2 times 1. So I can cancel out the 2's, I'm left with just effectively a minus 2. So what I get here is a0, 1 minus 2 xi squared. Oops, sorry, I forgot the xi squared here. I also forgot the a0. Times that's it for h2. h2 is this. If I want to calculate what the wave function psi2 looks like, it's going to be again this a0, 1 minus 2 xi squared multiplied by e to the minus xi squared over 2, our asymptotic solution. This is psi2, the second excited state, the third energy level. What we get if we plug n equal 2 into our framework here. So you can continue plugging in higher and higher values of n and using the appropriate 0 versus non-zero values of a0 and a1. So to check your understanding, use the recurrence relation as above to calculate not h2, that's too easy, I just did it for you. Calculate h3. So figure out what value of n you use to terminate, figure out which of the a0 or a1 have to be non-zero, and go through to determine the terms in the polynomial h3. These polynomials actually have a name. They're called Hermite polynomials, and they have enough mathematics surrounding them that we know a lot of their properties. There's, of course, more than 5 of them. There's an infinite set. And they obey the properties that you would hope they obey. There is an orthogonality relation, there is a normalization condition, etc. And given the standard definition like you get from textbooks or from Wolfram Alpha or from Mathematica for the Hermite polynomials, they have this normalization 1, 2, 4, 8, 16, 32 for the highest power. If we want to express our wave function in terms of these textbook definitions of Hermite polynomials, instead of the h's that I've been using, psi sub n as a function of x, which is going to be expressed in terms of xi, where x is root h bar over m omega xi. Putting all the normalization and all of the mathematical machinery together, you end up with something that looks familiar if you watched the lecture on solving this particular Schrodinger equation for this particular potential with ladder operators. M omega over pi h bar raised to the 1/4 power times something specific to the Hermite polynomials, a normalization to take care of the Hermite polynomial definitions, square root of 2 to the n factorial, multiplied by the nth Hermite polynomial as a function of xi, times e to the minus xi squared over 2. And this is our general expression of the stationary state wave functions resulting from power series analysis, expressing them in terms of Hermite polynomials instead of in terms of ladder operators acting on the sort of lowest energy, the ground state, the first solution, the lowest energy solution. So that's the power series solution to the time-independent Schrodinger equation for the quantum harmonic oscillator. We get an infinite series of states, and we get quantization conditions on the energy, where the energy of the nth state is given by h bar omega, oops, that's not an omega, h bar omega n plus a half, where n now is equal to 0, 1, 2, etc., up onto infinity. So we have a ladder of evenly spaced states now. Contrast this with the infinite square well potential, where we had energies that were proportional to n squared, and you start to see a little bit of the diversity of solutions that we get from quantum mechanics. The overall conceptual structure of the solutions is the same. You started with a wave equation, you apply boundary conditions and normalization conditions, and you restrict your set to a particular quantized set of energies. Then you express your stationary states in terms of the results of all of your mathematical analysis. That's the general procedure that you follow in terms of finding stationary states. This is the story all about how the Schrödinger equation applies to the free particle. What do we mean by a free particle? Imagine an electron, for instance, floating in the vacuum of space. It never encounters anything. It never runs into anything. How that enters the Schrödinger equation is that there is effectively no potential anywhere. So the time-independent Schrödinger equation, and we're back to one dimension now, so don't think about a particle floating around in the vacuum of three-dimensional space. It's floating around in the vacuum of one-dimensional space. The left-hand side of our time-independent Schrödinger equation is the Hamiltonian operator applied to the wave function. This is in some sense the total energy, which breaks down into a kinetic energy component here with the momentum of the particle squared divided by twice the mass, and a potential energy part here, where V of x is the potential energy that the particle would have to be found at a particular location. In the context of the free particle, where there is no potential, what that means is that V of x is equal to 0 everywhere. That means we can just cross out this term entirely. We don't have to worry about it. What we're left with then, for our time-independent Schrödinger equation, is minus h bar squared over 2m times the second partial derivative of psi with respect to x equal to e psi. Now, we have some constants here, and we have a constant here, so let's lump them all together. And I'm going to shift the signs around a little bit as well, so that what we've got is the second derivative of psi with respect to x is equal to minus 2me over h bar squared times the wave function. So just lumped all our constants together and multiplied through by a minus sign. Now, you notice the second derivative here of the wave function, giving you the wave function back. The fact that we're taking a second derivative suggests that the constant here perhaps is squared. So what I'm actually going to write this as is the second derivative of psi with respect to x is equal to minus some constant k squared times the wave function, where k, our constant, is the square root of 2me over Planck's constant. So this is a differential equation, and we ought to be able to solve this. This is relatively simple compared to the structure of the differential equations we got from the harmonic oscillator. So how do we solve this? Well, what we have, second partial of psi with respect to x, is minus some constant squared times the wave function. Taking the second derivative gives you a constant squared. That immediately suggests we look for exponential solutions. And it turns out the general solution to this equation is some constant times e to the minus I k x plus b e to the plus I k x. If I take the second derivative of this exponential term, I'll get a minus I k squared, which you know is just minus k squared, applying the rules of complex numbers, which is what we get here. So when I take the second derivative of this term, I'll end up with minus k squared times this term. And I get the same sort of thing here. If I take plus I k squared from the second derivative, that again gives me a minus k squared. So we're okay. This is our general solution. When we include time in this, since you know this is a solution to the time-independent Schrödinger equation, it's going to have time dependence given by the time part, the time equation that we got when we did separation of variables. What you end up with is psi of x and time now is equal to a e to the minus I kx times e to the I energy t over h bar plus b times e to the I kx e to the I energy time over h bar. And I've left off my minus signs here, in the energy dependence, just conventional to include minus signs there. We can rewrite this a little bit as a e to the I k. Now, what I'm doing here is substituting in the definition of k, which if you remember was the square root of 2m e all over h bar, expressing energy in terms of this k. And when I do that, what I end up with is this term ends up looking like h bar k squared over 2m. Substituting that in here is what we get from manipulating our constants. If I do that manipulation, the first term here, instead of having this product of two exponentials, I'm going to write it as a sum in the exponent, x minus h bar k over 2m t, plus b times something that looks very similar, e to the minus I k x plus h bar k over 2m t. So these are our general solutions to the full Schrodinger equation. Our full wave function is a function of both position and time. And these solutions are traveling waves. You can think about this as a traveling wave in the context of looking at this as a complex number. If I look at e to the ikx, for instance, as a function of x, you know what that does in the complex plane? It just rotates around in the complex plane. If I look at this as e to the ikx, let me redo that a little. Ik times x minus h bar k over 2m t. And I treat this as a function of time. Again, we just get rotation in the complex plane. We get rotation in the other direction, but that's not really all that important. What is important is that you can visualize this in, if you want to think about it in 3 dimensions, with some real part here, and, why do I say real and then write imaginary? With, say, the real part here and the imaginary part here. What we've got is something that spirals around the 0 point. Now, if I look at this as a function of both position and time, at every time I have this spiral as a function of position, say. As time increases, what changes about this spiral is the whole thing shifts, either in the plus x direction or in the minus x direction. And you can determine how that propagates by looking at the argument here. If I look at x minus h bar k over 2m t, if I'm looking for a specific point on the spiral, say this point, and I want to know whether it moves this direction or this direction, I can look at this expression here. This specific point on the spiral, as the spiral moves, is going to be represented by a constant value of this argument. And if all I'm caring about is what direction the wave moves, I might as well set that constant equal to 0. What that means is I can write this as x equals h bar k over 2m t. And this immediately tells me that as time increases, x increases for this specific point on the spiral. So in this particular case, the wave is going to the plus x direction. For the other term here, the relative sign of x and t is different, so you end up with a wave propagating in the opposite direction. So these are our traveling wave solutions to the time-independent Schrodinger equation, or to the overall Schrodinger equation, To check your understanding, go back and review the definitions of these traveling wave solutions, and think about how the energy enters. Do high-energy free particles move faster or slower? Is the wavelength, in a sense, the tightness of the spiral, shorter or longer? And is the time evolution, the rate at which the spiral rotates in time, faster or slower? What we did after we got our stationary state solutions to the Schrodinger equation for instance, the particle in a box or the harmonic oscillator, was examine the boundary conditions and determine whether or not we had quantization. This is where the free particle gets a little bit difficult to work with. The problem here is that v of x is equal to 0 everywhere. And I mean everywhere. There are essentially no boundaries. The fact that we have no boundaries means that we can have any value of that constant k, which means we can have any value of the energy, E. So we have no quantization here. That's a problem. It's not necessarily a problem directly, but it means that instead of what we were dealing with the particle in a box, for instance, where we had functions that were easy to represent, because there was a finite number of them, we could write a sum from n equals 1 to infinity of Cn times psi sub n. Same for the harmonic oscillator. We got a discrete set. We got a quantized solution. Now we have no quantization. So the framework that we built up for treating particles with quantized states isn't going to just directly apply. We'll have to do something a little different. The other thing that's different about the free particle is the normalization. The normalization condition we had for a wave function psi was that you multiply the complex conjugate of the wave function times the wave function itself, integrate from minus infinity to infinity, and I've left off my dx here. You should get 1. What happens when we do that here? Well, this normalization integral, if we're working with just say the term a times e to the, where did it go? E to the I k x minus h bar k over 2m t. If we're just working with this term, taking the complex conjugate is easy. The only complex part is this I here. And what we're going to end up with for our integral then, a being a constant, we can pull it out front, both the a star from psi star and the a from psi. We have the integral from minus infinity to infinity, dx, of the complex conjugate of psi, where we flip the sign here, and we've got e to the minus I k times something, which I'm too lazy to write. For psi, we get e to the plus I k times something that I'm too lazy to write, and it's the same something. These two terms, the arguments here, are the same, which means here I have a complex number times its complex conjugate. Since it's a complex number of modulus 1, I know this product is just going to be 1. So what I've got then is a star a times the integral from minus infinity to infinity dx, period. I'm done. And when you integrate dx from minus infinity to infinity, you get infinity. So this is a problem. These states are not normalizable. Anything I might do to try to normalize these by, say, setting this equal to 1 and solving for a, I would get a equals 1 over infinity, for instance. This is not useful. We cannot effectively normalize these states. This sounds like it has shot all of our framework in the foot, but it actually hasn't, because we can still use the framework of superposition. Superposition of these traveling wave solutions can give what are called wave packets. The bottom line, we can still write psi of x t equals 0 is a superposition of these traveling waves. We just have to be very careful about how we do the superposition. What these wave packets look like in the end, if I give myself an axis, is the wave function, the real part, might look something like this, where it's 0 for very large positive and very large negative values of x. The imaginary part might look something like this, where the full wave function only is non-zero over a specific interval. Over a limited range, for instance, or a limited domain, to use the mathematical term. When psi is only non-zero over a limited range like this, we can normalize it. What's tricky is how we normalize psi by making a superposition of non-normalizable states. And that's the topic for next lecture. So to check your understanding, here's a recap of what these traveling wave stationary states look like and what their properties. I promised in the last lecture that the solutions we got to the time-independent Schrödinger equation for the free particle, though they are not themselves normalizable and therefore cannot represent physically realizable states, could be used to construct physically realizable states. What that means is that we can take those solutions which themselves are not real and can add them up in a way that we can make something that is real. This is a little subtle. We're constructing something called a wave packet, and basically what that amounts to is adding up a bunch of infinities and getting something finite. Taking these traveling wave solutions to the time-independent Schrödinger equation for the free particle, which extend from -infinity to infinity in the spatial domain, and from -infinity to infinity in the temporal domain, and summing them up somehow to get something that is localized in the spatial domain. What that means is that we're making a wave packet. A wave packet, the features that we care about is that it's going to be 0 for, say, large negative values of x, 0 for large positive values of x, and only non-zero over some domain. What it might look like is, well, 0, some wave activity over a relatively limited region, and then going back to 0. We will see wave packets that look like this later on. I'll give a more concrete example and show some animations. But for now, let's think about the math. How would we go about constructing something like this? What we did in the case of the particle in a box, the infinite square well potential, was when we solved the Schrödinger equation, we got solutions. If our potential looks like this, going to infinity at regions outside of a box, our solutions looked like this. We got sinusoids with an integer number of half wavelengths fitting in our box. That was nice because it allowed us to construct our overall solution to the Schrödinger equation, psi of x and t, as an infinite sum of these stationary state wave functions. The integer number of half wavelengths fitting in the box, plus the essentially trivial time dependence that you get from the time equation when you do separation of variables with the general Schrödinger equation. This isn't going to work for the case of the free particle for a couple of reasons. First of all, instead of having a discrete sum over, states which have an index n, for instance, this is our psi sub n, where n goes from 1 to infinity, we now have wave functions psi that are continuous. We did not have quantized states. So our stationary states now are going to have to look like our traveling waves. They're going to have to look like e to the I, k, and then x minus, where did it go? h bar k over 2m t. This was our traveling wave solution from the last lecture. So instead of having our discrete set of states indexed by n, we have our continuous set where the parameter is k. K is a completely free parameter, not fixed to be an integer. The second reason our machinery for the particle in a box won't quite work is this coefficient c sub n. C sub n is also going to have to somehow become a function of k. K now being unrestricted, we can't just treat it as a set of discrete entities. We have to have some function. And that function is conventionally written as phi of k. And finally, this sum out front. Again, we can't do a sum if we have a continuous set of functions that we're working with that we want to add up. We have to do an integral. The integral now is going to be an integral over k. So our sum over n became an integral over k. Our coefficient, subscript n, became a function of k. And our discrete set of functions, psi sub n, became these traveling wave solutions with the parameter k in them. Our integral dk goes over all the possible values of k from -infinity to infinity. And this is what the expression is overall going to look like. We have an integral, we have this continuous function, and we have our traveling wave states. The main problem with this expression is this guy. How do we know? How do we find phi of k? Phi of k is a general function. What we had done to find the analog of this was at c sub n in the case of the particle in a box. What we did for the case of the particle in a box was use Fourier's trick to collapse the sum. Instead of a sum now we have an integral, and it's not immediately clear from looking at this what it means for an integral to collapse. We'll see what that means in a second. But first of all, let's go back to what we did in the case of the particle in a box and spell out some of the details so that we can make an analogy. On the left-hand side here now we have the results for the particle in a box, whereas on the right-hand side we have the results as I have outlined what they might look like for the free particle. So the first thing we did for our particle in a box was to express the initial conditions as an infinite sum of the time t equals 0 form of our stationary state wave functions. The second thing we did in manipulating this expression to attempt to find a formula for the c sub n was to multiply on the left by a particular stationary state wave function, not n, m. So we multiplied by root 2 over a sine m pi over a x psi of x 0. This is now looking at the left-hand side. So we multiplied by this, and we integrated from 0 to a. This integral is taken dx. It's important to note now that this is not the wave function psi, this is the complex conjugate of the wave function psi, and we'll come back to that in a moment. This integral, this is our left-hand side. If we do the same thing to the right-hand side, you end up with an integral dx that you can push inside the sum, you can pull out some constants, and all you're left with then, the only x dependence comes from the sine function here and the sine function you're multiplying in. So we ended up with the sum from n equals 1 to infinity of c sub n, our two root 2 over a factors from our two wave functions multiply together, just give us 2 over a. And what we're left with inside the integral is sine of m pi over a x sine of n pi over a x dx. So that was our expression. And the nice feature about this is that the sine functions had an orthogonality condition on them that allowed us to take this integral from 0 to a and express it as delta mn. The sine functions, if m is not equal to n, will integrate to 0 over this interval. And if m is equal to n, you just end up with 1. I should be including this factor out front in the expression for the orthogonality. What that means is that the sum collapses. The only remaining term is the term from Cm. So our right-hand side just becomes Cm. This gave us our formula for Cm being equal to the integral from 0 to a of essentially root 2 over a sine m pi over a x times our initial conditions, psi of x 0. This was a very brief overview of what we did back when we were talking about the particle in a box. Now, continuing this analogy into our free particle case, again, the first thing we're going to do is left multiply by the complex conjugate of the wave function. Now, the wave functions that we're working with now are stationary state solutions to the time-independent Schrödinger equation for the free particle. And what those look like, if I evaluate them at t equals 0, is e to the minus I kx. Now, I'm leaving off normalization constants because I don't know what they are at this point, but while I have a k in this integral, I shouldn't use k here. This is the same as saying I have an n in this sum, so I shouldn't use n in the function that I'm multiplying through. Things will just get confusing. So I'm going to call this k prime. So I've left multiplied by k prime. I have my wave function, my initial conditions. And again, I'm integrating. Now I'm integrating from minus infinity to infinity. And I'm integrating dx. This is what I get for the left-hand side, just following by analogy from what we did for particle in a box. The right-hand side, in this case, now instead of having a sum over n, I have an integral over k. What I'm multiplying by from the left is again the e to the minus I k prime x, but this integral that I'm doing, that's an integral dx. So I can exchange the order of integration by k and integration by x. So I'm going to write this right-hand side now a little differently. We have the integral of minus infinity to infinity dk. Then we have phi of k, which is not a function of x, so I can pull it out of my integral over x, same as I could pull my c sub n out of this integral dx. Sorry, phi of k, not phi of x. What I'm left with then is the integral from minus infinity to infinity dx, e to the minus I k prime x, e to the I k x. Now, in order for this term to be meaningfully, or in order for this integral to collapse, like the sum collapsed here, we have to have some sort of orthogonality condition. The orthogonality condition for the sine functions from 0 to a was fairly straightforward. The orthogonality condition that applies here for this, where we are integrating over an infinite domain of something with a continuous parameter, k prime and k are continuous parameters that can take on any value, is not a simple Kronecker delta. It's a little different, but it looks very much the same. What you end up with here is called a Dirac delta function. And we will meet these Dirac delta functions in more detail later. If you're interested, there is a video lecture posted on the Dirac delta function and what its properties are. But for our purposes here, this expression evaluates to a Dirac delta function. A Dirac delta function is defined essentially as an infinitely narrow distribution. If you treat this as a distribution that only is non-zero at a particular value, the delta function by default is defined to be non-zero only for its argument equal to 0. This is effectively a distribution that only has non-zero values, only has support for k equal to k prime. If you treat this as a distribution, and you examine the expression integral from minus infinity to infinity dk of phi of k, delta of k minus k prime, if this is a distribution, we're integrating a distribution times a function. This is the expected value of phi of k, subject to the distribution given by the delta function. The delta function, acting like an infinitely narrow distribution, then simply pulls out the value that phi of k has when k equals k prime. Since this is infinitely narrow, phi of k is effectively a constant over the non-zero domain of the delta function. So it's just effectively averaging a constant over this domain. So this, a whole integral here, is equal to phi of k prime. That's what it means for an integral to collapse. And like I said, if you're not entirely clear on how the delta function works, there's another video lecture on how to go about, or how to understand what the delta function can do for you. For now, notice that we can re-express this phi of k prime then in terms of our left-hand side. Phi of k prime is equal to the integral from minus infinity to infinity of e to the minus I k prime x psi of x0 integral dx. This completely determines phi of k. This is the real genius behind what's called Fourier analysis. What we were talking about in the case of the particle in a box was really Fourier series. And now we're talking about Fourier analysis. The way the math behind this is usually defined is in terms of something called the Fourier transform. The top two equations here are essentially definitions of the Fourier transform. We have some function of x. This is like our wave function as a function of time, and it's being expressed as an integral of some function of k multiplied by e to the I kx, integral dk. This function f, capital F of k, can be determined by essentially what we did in the previous slide, an integral from minus infinity to infinity dx of the function lowercase f of x times e to the minus I kx. The 1 over root 2 pi factors here are customary. Some authors use them, some authors define them slightly differently. It depends on the specific definition of the Fourier transform that you're using. But you can see the nice symmetry between these two equations. You have your 1 over root 2 pi in both equations. You have an integral from minus infinity to infinity in both equations. You have e to the I kx here, positive, and e to the minus I kx here, negative. That's the only difference. Then you have a function of k, integral dk, function of x, integral dx. Up to labeling x and k differently, the only difference between these two equations is the sign in the exponent. There's a lot of really nice math that comes from using Fourier transforms. Just to give a very brief example, if you're interested in processing astronomical images, for example, or any images really, treating the image as a function of this k parameter, which is a spatial frequency parameter, instead of treating the image as a function of x, as a function of which pixel you're looking at, you can do some very powerful analysis to identify features, for instance. High spatial frequency features versus low spatial frequency features. Smoothly varying backgrounds versus the boundaries between objects where the image varies rapidly will have different behavior when expressed in terms of this function of the spatial frequency. From the perspective of quantum mechanics, what we're interested in is how to express our wave function as a function of position and time. Well, using the Fourier transform definition here, we can find this phi of k by the same sort of equation. Phi of k is determined by an integral dx of our initial conditions times a complex exponential. Knowing what phi of k is, we can then determine what phi of x and t is. So again, our initial conditions determine our constant multiples essentially of our stationary states, these complex exponentials, which then gives us our overall wave function and how it behaves. To check your understanding, here is a simple example problem that requires you to apply the formulas on the previous page to go from a particular initial condition. In this case, it's a constant. Our initial wave function looks something like this. 0 everywhere except for a region between minus a and a. Your task, find the phi of k that goes with this particular function. That's about it, but before we finish talking about how to superpose these solutions, I want to look at the solutions themselves in a little more detail. Let's talk about the wave velocity in particular. This is our traveling wave solution, and we can figure out what its velocity is by looking at this argument. Which direction is this wave going? Well, if we look at a particular point on this spiral, on this e to the I kx, as time evolves, we can figure out where that point on the spiral is by setting this argument equals to a constant. Since I don't really care about what that constant is, I'm just going to set that equal to 0. So let's say kx minus h bar k squared over 2m t is equal to 0. If I continue along these lines, it's clear that in this case, if t increases, this part of this expression is getting more negative. This part of the expression has to get more positive. So that means x has to increase as well. So as t increases, x increases. That means this wave is moving to the right. The next question I can ask is how fast? How fast is it moving? And if you look at this again as setting this expression equal to 0, I can solve this and say x is equal to h bar k over 2m t. And in this case, the velocity is pretty clear. We have this constant, x equals some constant times time. Position equals something times time. This is our velocity. What this actually is, in terms of the energy of the particle, requires knowing what the definition of k is. So we have h bar over 2m, and the definition of our k was root 2me over h bar. So our h bars cancel out, and if we finish this expression, moving the 2m effectively under the square root, we get the square root of e over 2mt. So the velocity we get here is square root of e over 2m. Now, classically, what we get, we have a particle moving at some velocity and it has some energy. We know the relationship between those. It's the kinetic energy, 1/2 mv squared, gives me E. And if I solve this, I get v squared equals 2e over m, or v equals root 2e over m. These expressions are not equal to each other. That's a little strange. The velocity that we got from quantum mechanics, looking at how fast features on this wave function move, is not equal to the classical velocity. Will this hold true regardless? Do quantum mechanical particles have a different propagation behavior? That doesn't really make a lot of sense. This is actually not a problem, because what we're measuring here is the velocity of a feature on this wave. It's not actually the velocity of a wave packet. And since wave packets are the only real states that we can get, that we expect to observe in the physical universe, what we need to figure out is the wave packet velocity. In order to figure out the wave packet velocity, consider this wave packet. This is just a sum of two traveling waves with different k's, which I've now indexed k1 and k2. What I'd like you to do is think about expressing k1 and k2 as if they were near each other. So k1 is slightly less than k2, for example, or k1 is slightly greater than k2. Under these circumstances, it makes sense to rewrite these things. I'm going to define alpha as k1 plus k2 over 2, the average, times x, minus h bar k1 squared plus k2 squared over 2m t. Essentially, the sum of the argument of this and the argument of this. I'm also going to define a parameter delta, which is k1 minus k2 over 2x minus h bar k1 squared minus k2 squared over 2m t. Actually, sorry, I don't mean 2m's here. I mean 4m's here. Because I have a factor of 2 from the over 2m, and I have a 1/2 essentially from the way I'm combining the two terms. So given these definitions, you can express this as as e to the I alpha plus delta plus e to the I alpha minus delta. So you see what I've done here? I've just re-expressed the arguments here as sums and differences. This is getting into the idea behind sum and difference and product identities in trig functions, except I'm doing this with complex exponentials instead. If I write this function as alpha plus delta, when I add alpha and delta, for instance, this first term gets me k1 plus k2 plus k1 minus k2. The k2's drop out. and I end up with 2k1 over 2, which is just k1 times x. Just k1x, essentially. What you want to get from this, if I express these exponentials in that way, you can factor out the alpha part. You get an e to the I alpha times an e to the I delta plus e to the minus I delta. If you're familiar with the complex exponential form of trig functions, you can probably see where I'm going with this. This is going to end up equal to e to the I alpha times cosine. Actually, not just cosine, 2 cosine of delta. What this looks like in the context of our discussion of wave packets is if we have an axis there, we have this cosine factor, and it's the cosine of delta. If k1 and k2 are near each other, this will be a small number. This will also be a relatively small number. So delta evolves much more slowly with space and time than alpha. So if I was going to draw this wave function, I would have some slowly varying envelope like this, and superposed on top of that, multiplied by that slowly varying envelope, is e to the I alpha, which is the sum. So if k1 is close to k2, this is going to evolve much more rapidly. So my overall wave packet is going to look something like this, where you have zeros and areas with large amplitude, areas with small amplitude, areas with large amplitude, areas with small amplitude. As time evolves, this wave packet will propagate. And if what we're interested in is the velocity with which the overall packet propagates, you can consider a point on delta, not a point on alpha. If we're interested in the velocity with which these rapidly moving peaks, rapidly oscillating peaks evolve, then we would look at alpha. But since what we're interested in now is the wave packet, we want to look at delta. We want to look at the slowly varying envelope, how quickly the slowly varying envelope moves. Now, I haven't actually constructed a fully formed, physically realizable wave packet here because I have this cosine term, which again extends all the way from minus infinity to infinity. But hopefully, conceptually, you can think about this as a sort of rudimentary wave packet. The question then is, how fast does the rudimentary wave packet move? Well, if I look at delta, and if I assume that k1 is near k2, we can see how that works out. So what I'm looking at here is delta is equal to 0, say. The same sort of argument that I was using to determine how fast a feature on a single wave moved, setting this delta equal to a constant, not caring what the constant was, and setting it equal to 0. What I get then is k1 minus k2 over 2x being equal to h bar over 4m, and then k1 squared minus k2 squared, I'm going to look at this as the difference of two squares, which I can factor k1 plus k2 times k1 minus k2. I can then cancel out this and this, and what I'm left with is just x over 2 equals to h over 4m k1 plus k2. If I assume that k1 is about equal to k2 then, I can pretend that this is some effective average k bar. If I write that out, this is 2 k bar, twice k bar, since I have k1 and k2, when they're added together. I can then look at this. I have a 1 over 2 here, a 1 over 4 here, and a 2 here. What I end up with at the end is just going to be x equals h bar over m times k bar. This is different than the expression we got before. K bar now is going to be our average k, h bar over m to copy that over, and our k was root 2m e bar now for k bar. Instead of k bar, I'll have e bar for my average. And then I have Planck's constant. I can cancel out Planck's constant in the denominator. I can again push my mass into the square root here. And what I'm left with then is root 2e over m times time. I forgot my times time here. All of these have a times time. So x equals something times time. This is our velocity. So here, for the wave packet velocity, we get root 2e over m. This is the classical velocity. So, problem solved. Whereas the features on each individual peak, for instance, in our wave function, traveled at one velocity, the overall wave packet traveled at another velocity. For the case of this particular wave packet, or wave packets in general, the wave packet itself travels at the velocity you would expect, except I have to be clear here now. Let me rewrite this. The velocity we get for a wave packet now, this is only approximate, so I should write it as approximately equals, and it's not twice the energy, it's twice the average energy divided by mass in the square root. So this is not exactly the classical formula because now we don't necessarily have a single energy. If we had a single energy, we would be stuck with one of those solutions to the time-independent Schrödinger equation, which have definite energy. In the case of this free particle, those definite energy solutions extended throughout all space, and that was a problem. So we don't actually have a definite energy, so we'll have some spread in energies here. And if you have a large spread in energies, you'll effectively get a large spread in velocities. And what starts off as a wave packet will not stay a wave packet very long. It will propagate at different speeds. Different parts of the wave packet will propagate faster than others. But at any rate, what this actually looks like, to make some visuals here, and I couldn't hope to draw this accurately, but if we have some wave packet at time t equals 0, delta t, 2 delta t, and 3 delta t, it's going to propagate gradually. You can see the disturbance of this wave moving to the right. Now I've drawn solid, thick lines here behind it to designate the motion of the overall wave packet. The overall packet is moving at a speed more or less determined by the slope of these thick black lines. The thin gray lines identify features. For instance, this peak becomes this peak, becomes this peak, becomes this peak. This peak is traveling at a more slow rate than the overall wave packet and is essentially sort of falling off the back of the packet. It's decreasing in amplitude as it goes. The slopes of these lines are different, meaning the features on the waves are propagating at a different speed than the overall wave packet. This is actually a general feature of many waves. It's not something we hear about very often in everyday life because we never really think about whether there might be a difference or not. Plus, most of the common waves that we work with, like sound waves, for instance, don't have this property. But if you look closely, for instance, if you drop a rock in a still pond, the small-scale ripples actually behave with this different velocity. In that case, actually, the features on the wave move faster than the overall wave packet. So in that case, you could view this as sort of time reversed, where the features start at the back of the wave packet and propagate forwards. But this is really the question of what's called group velocity and the question of phase velocity. The phase velocity refers to the features in the wave, whereas the group velocity refers to the velocity of the wave packet. This is not a wave mechanics course, but there's a lot of interesting math that can be done with this. The group velocity and the phase velocity being different is one of the more interesting features of, for instance, propagation of electromagnetic waves in plasmas in space. So if you're interested in radio astronomy, for instance, you need to know about this in very high levels of detail. To give you a better feel for what this looks like, here's an animation. What we're looking at now are the real and complex parts, shown in red and blue, respectively, of a hypothetical wave packet that might represent a solution to the Schrödinger equation. It doesn't actually represent a solution to the Schrödinger equation, but this is the sort of behavior we're looking at. If I track a particular pulse, say this one, I'm moving my hand to the right as I do so. Here. But I'm not moving my hand to the right nearly as fast as the overall wave packet is propagating. So the overall wave packet is propagating at effectively twice the speed of the individual features on the wave. So this is what wave propagation might actually look like for the Schrödinger equation. You can construct wave packets like this. If you add the time dependence, then you can determine how the wave packet will propagate, how it will spread out, how the individual wave features will move, and you'll know effectively everything you need to. To check your understanding, here are a few true or false questions. Don't think that because they're true or false, they're easy. Think about these in detail. Our discussion of free particle stationary states, traveling waves that are infinite in extent and therefore not normalizable, led us to the concept of a wave packet and the results of Fourier analysis that described how we could superpose these infinitely extended traveling wave solutions to make something that was localized and therefore normalizable. To give you a feel for what these look like, here is an example. The initial conditions we're going to consider here are something we've seen before in class. The wave function psi evaluated at t equals 0 is given by this conditional expression. You have a normalization constant out front, and then you have values for a x between minus a and 0, between 0 and a, and everywhere else is 0. What this actually looks like is from, say, minus a to a, our wave function is a triangle. And outside of those regions, our wave function is 0. So this is now psi of x at t equals 0. If this is our wave function, hopefully you remember what the probability density as a function of position looked like at time t equals 0 as well. Between minus a and a, it sort of looked like two parabolas joined together. So how would we go about expressing this initial condition as a superposition of these infinite traveling waves? The result from Fourier analysis we're using now is the expression for the phi of k, the representation of the wave function in terms of k, where k is related to the energy and the spatial wavelengths of the traveling wave. What this actually looks like, we have to substitute in our definitions. We have a 1 over root 2 pi, as before. From our initial conditions, we have the normalization of the initial conditions, 3 over 2a in a square root sign. And then our initial conditions are split up between the region minus a to 0 and 0 to a. So let's split up our integral from minus a to 0, and again from 0 to a. And we'll be adding these two integrals together. These are going to be integrals dx. I'm just splitting up this integral here. And what we actually have inside our integral, since we're looking at the t equals 0 version of the complex conjugate of the wave function here, e to the minus ikx is all we've got to work with for our traveling wave. And our initial conditions enter in from just the spatial dependent part. So we have a plus x over a from the space from minus a to 0, and then our e to the minus ikx from here. And for the space from 0 to a, we have a minus x over a, and then again e to the minus ikx dx. This is the integral that we wish to evaluate. These integrals are not as difficult as they might seem, because they're all of the form either e to the minus ikx or x e to the minus ikx. This can just be directly integrated. This is a candidate for integration by parts. So those would be the techniques that we would use, and if I had the patience to work through the page or so of algebra, what we actually end up with here are phi of k ends up being sine squared of x over x squared. Related to this, it's not going to be exactly x, but this is the sort of functional dependence that we have. Sinc squared, if you're familiar with the definition of the sinc function. Here's what that looks like. This is phi of k as a function of k, or phi as a function of k. So our x-axis here is k, and our y-axis is phi of k. The sinc squared function here is symmetric between negative and positive values of k. What this means from the perspective of the traveling wave solutions is that phi of k, which tells us how much of each traveling wave solution we are going to add up to get our overall wave function, we effectively have equal contributions from left-going waves and from right-going waves. So overall, maybe we expect our wave function not to be moving. Knowing what phi of k is, we can go back through taking the inverse Fourier transform to find out what psi of x and t is, because we know the time dependence of these traveling waves. The inverse Fourier transform then is going to give us psi of x and time, including the time dependence, in our traveling wave solutions now. So we have 1 over 2 pi times the integral from negative infinity to infinity of this phi of k that we got from the previous slide. This is going to look like sine of k, sine squared of k over k squared. So we have a function of k, we have another function of k, and the integral here, which I left off in the actual notation, is dt. So in principle, if we had something here that we could easily integrate, we could find psi as a function of t. Unfortunately, closed-form integrable solutions to this equation are hard to come by. The example I've chosen here, you can probably guess that we're going to end up in trouble because the initial function that we started with, our initial conditions, was defined piecewise. And it's difficult to imagine a closed solution like this that gives us anything sensible that we can work with in the piecewise manner. So, at this point, we could in principle do this integral, but I'm lazy. So let's go and look at what the solutions actually look like. I went through and did these integrals numerically using Sage, and here's what you end up with. The initial conditions, the real part of the wave function is shown in red now, the imaginary part shown in blue. So when this animation loops, there's your initial conditions, and gradually things get smoother, decay away. You start to see things that look like traveling waves propagating to the right and propagating to the left. If I look at this instead in terms of the probability density, this is now a plot of the squared modulus of the wave function as a function of time. The initial conditions look like those joined parabolas there, but gradually things spread out, starts looking like a Gaussian, and the probability density gets broader and broader and broader and broader. So this is what wave packet solutions to the time-independent Schrodinger equation, or for the full Schrodinger equation, for the free particle actually look like. Your initial conditions are expressed as a superposition of stationary states, these traveling wave solutions, with the results from Fourier analysis. Taking the inverse Fourier transform of the representation in terms of stationary states allows us to easily add the time dependence, since we know the time dependence of each stationary state. The final solutions then are often tricky to work with, but in this case we could do something numerically relatively easily, though it did take a bit of CPU time to do these integrals, and you get a feel for what the wave function of evolution actually looks like. To check your understanding, here are a couple of questions. I've gotten sloppy with my notation. This is phi of k, the Greek letter, not phi of k. But first question, the wave function represented in terms of k is symmetric. Phi of minus k is phi of k. What does that imply about the direction of propagation of the particle or of the wave function? And second of all, you have some spreading out in space. Does the representation of phi, or this representation of the wave function in terms of k, which is related to the momentum, it's often called the momentum representation, also spread out as time increases. We've already met the Dirac delta function a couple of times in this course as examples. So it's good at this point, since what we're going to be discussing next is the Dirac delta function as a potential, to discuss the general properties of the Dirac delta function, how it works from the mathematical perspective. What I want you guys to think of when you think of the Dirac delta function is the limit of a distribution. The Gaussian distribution, for example, rho of x is given by 1 over the square root of 2 pi as a normalization, sigma, e to the minus, say, x squared over 2 sigma squared. The limit as sigma goes to 0 of this function gives you something that is very much like the delta function. This is not the only way to define the delta function, but if we start with, for instance, this purple curve here at large sigma, and this orange curve here at small sigma, as sigma gets smaller and smaller, the distribution gets narrower and narrower and taller. As sigma gets smaller, for instance, the dependence here in the exponent of e to the minus x squared gets faster and faster, since I'm effectively multiplying the x squared by a larger and larger number. And the normalization constant out front, 1 over root 2 pi times sigma, gets larger and larger as sigma gets smaller and smaller. So thinking about this as the limit, in the limit, we have a distribution that is infinitely narrow and infinitely tall. It has absolutely no support for any values of x other than, say, x equals 0 here. So this would be, say, delta of x as a distribution. You often see delta functions written as, in terms of more conventional function notation, delta of x is equal to 0 for x not equal to 0, and infinity for x equals to 0. But this isn't a sufficiently accurate description because it doesn't tell you this property that the delta function is the limit of a distribution. It has specified integral. So you always have to add an extra condition here for something like, for instance, something like the integral from minus infinity to infinity of delta of x dx is equal to 1. That essentially sets the specific value of the infinity here such that the integral equals 1. But thinking of it as the limit of a distribution is essentially the actual definition of the delta function. Knowing that the delta function acts like distribution allows us to do things like calculate integrals with delta functions. This is where delta functions really shine. If you have an integral of minus infinity to infinity of any function, f of x, multiplied by the delta function, if we think of this as a distribution, this is effectively the expectation of x, of f of x, the expected value of f of x, subject to this distribution given by the delta function. Now, since the delta function has absolutely no support over any values of x other than x equals 0, essentially what this is telling you is the expected value of f of x, where the only region that we care about is the area very near 0. So this just gives us f of 0. Thinking about this in the context of a distribution, if we had a distribution with some very narrow width, if this width gets extraordinarily narrow, then no matter what f of x does out here, we don't care. And as the distribution becomes extraordinarily narrow, we're just zeroing in on the behavior of x over this region, which makes f of x basically look like a constant. And you know, the expected value of a constant, like if I wrote this as the expected value of f of 0, it wouldn't matter what the distribution was, it would just give you f of 0. So this is the same sort of concept. The infinitely narrow distribution effectively just pulls out the value of f of x at that point. So this is our first really useful formula with delta functions. If we integrate, doesn't really matter what we integrate over, minus infinity to infinity will work. Delta of x times any function f of x integrating dx, we just get f of 0. We don't have to do the integral. Delta functions effectively make integrals go away. We can do this not just for the delta function delta function of x, we can do it for delta functions of x minus anything, for instance, x minus a. If we plotted this distribution, delta of x minus a, it's going to be 0, except for the point where x equals a. So at x equals a, the argument is delta function goes to 0. So effectively, we've just translated our delta function over by some distance a. Not the most clear notation. This is the x-axis and this is a. So what this is going to do, and you can think about doing a change of variables, some sort of u substitution where u equals x minus a, it's just going to give you the value of f at the point where the delta function has support. So this is going to give us f of a. So if we have some way of expressing the delta function, or if we're just using the delta function itself translated, we can pull out the value of f at any point. We can do more with this, though. Instead of just subtracting values in the delta function, we can evaluate the delta function of a function. Again, what we're working with here is integrals multiplied by some other function, since that's how delta functions most often appear in this context. So, if I have coordinates, and what I'm interested in now is g of x plotted as a function of x, suppose g of x looks something like this. I have some places where g of x crosses the x-axis, where g of x equals 0. I know the delta function is going to be 0 for any argument that's non-zero. So essentially what this is going to do is home in on these regions where g of x is equal to 0. And I drew 5 of them here. Doesn't really matter how many there are, but every time as we scan through an x, say calculating this integral, every time g of x goes to 0, we'll have support from the delta function. And it will effectively pull out something related to the value of f of x at that point where g of x goes to 0. Now, if you consider a g of x that looks, let me draw a slightly more exaggerated form here. Suppose g of x look something like this. We have 2 points where g of x crosses 0, but g of x crosses 0 at different rates. Now, if I thought of the delta function as the limit of a distribution that's not infinitely narrow, but has some finite width to it, I could think about the values, the regions where g of x is between 2 small values, one slightly positive and one slightly negative. And if you look at some region like this, if I zoom in on this, you have g of x crossing with a steep slope, crossing your axis, and then you have your region between which the delta function of g of x will be non-zero. And if you look at the coordinates here that span that range, you'll get a fairly narrow window. You'll get a much narrower window than if you consider something like the other point here, where g of x crosses the axis, but at a much shallower angle. Now, if I'm concerned with that region over which delta function has non-zero value, it's going to be much broader. We're going to be dealing with a much broader range in x than if and then g of x crosses the x-axis at a more steep angle. Essentially, what I'm trying to argue here is the slope of g of x as it passes the x-axis is what determines the effective width of the delta function. Now, treating the delta function as a distribution now isn't necessarily as valid, since the overall distribution here isn't necessarily normalized. Delta of x is normalized, delta of g of x is not necessarily normalized. The range over which the delta function has support then will be related to the effective distribution, delta of g of x. For instance, here, if g of x crosses at a very shallow angle, the delta function has a broader region of support and therefore is going to effectively pick out a more heavily weighted value of f of x. F of x is still going to act like a constant here. Suppose I have some f of x that I'm multiplying in here, and it looks maybe something like that. F of x is still going to act like a constant, but I'm going to be multiplying the value of f of x at this point by a relatively smaller window than if I'm multiplying the value of f of x at this point. All of this is just a conceptual argument for the form of this function. Delta of g of x is typically written as a sum, and I'll write as a sum over I, of delta of x minus x sub I over the absolute magnitude of the derivative g prime evaluated at x sub I, where these x sub I are the zeros of g of x, the points where g of x crosses the axis. So this would be maybe x sub 1, and this would be x sub 2, in this case, if g of x has two zeros. The effective slope of g of x evaluated at the point where g of x crosses the x-axis, where g of x is 0, tells you effectively how things are weighted. That's what I was trying to argue with this slope and the effective width of the delta function at that point. So factoring this out here, writing this factor here in the denominator, g prime of x sub I accounts for that. Steeper slope results in smaller effective window. Larger derivative, steeper slope, results in smaller effective contribution to the overall delta of g of x. To give you an example of how this works, consider delta of ax plus bx squared. I can simplify that a little bit, writing it as delta of ax times times 1 minus b over ax to factor things out. Factoring this makes it very clear that this is going to have zeros at x equals 0 and x equals a over b. If those are our zeros, then this means I have something, let's call this x1 and this x2, that I can use in this formula. So now I need to figure out if this inner quantity here is g of x. What's g prime of x? Well, this is a simple polynomial, so taking the derivative is pretty easy. We get a plus 2bx. Oops, sorry, I've dropped a minus sign here. Let's make that a negative. Let's make that a negative, just for the sake of correctness. The second formula I wrote here was correct. That minus sign didn't just magically appear from nothing. So I know what my x1 and my x2 are. I know what my derivative is. I can evaluate my g prime of x1, and x1 is 0. I evaluate g prime at x equals 0. The second term just drops out, and I get a. I can also evaluate g prime of x2, and if I substitute in a over b for this, I get a over b, and for x here, the b's cancel out, and I'm left with a minus 2a. I get minus a here. So you've got the same effective magnitude of the derivative, which is what's going to be important here. And that should make sense, since the function here, g of x, is just a parabola, looks something like this, between 0 and a. No, sorry, not 0 and a, between 0 and a over b. So substituting in here, we can write this overall, delta of ax minus bx squared is equal to delta of x, where I'm looking at x minus x1, where x1 is 0. So delta of x minus 0 over the absolute magnitude of a, plus delta of x minus a over b divided by the absolute magnitude of minus a, which is just going to be the absolute magnitude of a. So evaluating the delta function of something in an integral context like this allows you to make a transformation to express the delta function as a sum of delta functions delta functions shifted over to where the function that you're evaluating the delta function of, g of x here, equals 0. Keep in mind you're always going to be working with delta functions in this integral context, even when you're working with delta of g of x. So it's not necessarily terribly meaningful to look at this sort of thing, delta function of a function. This sort of transformation is really only going to be useful when you go and substitute it back in when you have some sort of an integral. So let's do another example. Delta function of x cubed minus x times e to the minus x. The g of x we're working with here is x cubed minus x. So I can take the derivative, g prime of x, that's going to be 3x squared minus 1. I can also rewrite g of x as x times x squared minus 1, which I can continue to factor x plus 1, x minus 1, factoring this as the difference of two squares. So that allows me to re-express my delta of x cubed minus x as I have just 3 zeros from this. x1 equals 0, x2 equals minus 1, and x3 equals 1. So I can express it as a sum of 3 delta functions. Delta of x over effective derivative here, which I'll write in a moment, plus delta of x minus 1 over its effective derivative plus, or over the effective derivative of g of x here, plus delta of x plus 1, again over the magnitude of the derivative of g of x. And if you go through and evaluate the magnitudes of the derivatives here, you end up with minus 1 here, 2 here, and 2 here. So this is our overall formula. So what we're going to be integrating then is the integral from minus infinity to infinity of this re-expression of our delta function, delta of x plus delta of x minus 1 over 2 plus delta of x plus 1 over 2, all multiplied by our function e to the minus x dx. Now these are just simple delta functions multiplied by your secondary function. You know, these are infinitely narrow normalized distributions now. I've gotten rid of the function inside the delta, re-expressing it just as translated deltas. Which means what you get when you do this integral is just the value of e to the minus x at x equals 0, the value of e to the minus x at x equals minus 1, the value of e to the minus x at x equals minus 1, plus 1 from this one, minus 1 from this one, with these appropriate normalization constants multiplied in. So evaluating e to the minus x at x equals 0, that's just 1. Evaluating e to the minus x at x equals plus 1, that's just e to the minus x, so I'm adding e to the minus x over 2 from the over 2 here, plus, again, the value of e to the minus x at minus 1, which is just e to the x over 2. That's our answer. We're done. No actual integration required. To check your understanding here are a couple of integrals for you to do. Translated delta function, simple g of x inside the argument of the delta function, and slightly more complicated but still factorable argument of the delta function. None of these integrals should be difficult. None of them actually requires any integration. This is just to give you a feel for working with the sorts of functions that we'll have to work with in quantum mechanics, for example. You can also take derivatives of delta functions, and the derivative of the delta function is a strange thing to think about. If I have a delta function, thinking about it as the limit of a very narrow distribution, I have sort of a positive derivative on one side and a negative derivative on the other side. So the derivative that I'm going to be working with then, if this is delta of x, and I'll put that in quotes because delta function is of course the limit where it's infinitely narrow and I can no longer meaningfully draw it, the derivative, delta prime of x, for instance, which, well, I don't really like writing it as delta prime. Let's write it as d delta dx, that's a function of x, is going to be positive, negative, and back to 0. In the limit where the delta function becomes infinitely narrow, these positive and negative excursions are going to become infinitely narrow as well. And you can think, well, it's sort of taking the positive side of a function. If this is going to act like a delta function, it's going to be like x from the function that we're integrating the derivative of the delta function with from the positive side, and then we're going to be, or with a minus sign, we're going to be adding on the value of the function from the negative side. So value from the positive side, value from the negative side, all added up with a minus sign on one and a plus sign on the other. That sort of looks like taking the derivative. And you can see that by looking at this expression and thinking integration by parts. For instance, if I say u, that's going to be f of x, and dv, that's going to be d delta dx dx. I can do integration by parts. My du is going to be df dx times dx, and my v is going to be delta. When I integrate the derivative of the delta function, I'm just going to get the delta function back. So my integration by parts for this expression is then going to tell me my term without any derivatives in it, f of x, delta of x, evaluated the limits of my integral, in this case minus infinity to infinity, minus the integral of the terms with derivatives in them. I'm just going to get delta of x, integrating again from minus infinity to infinity, delta of x times df dx integral dx. And, well, our boundary term here, f of x times delta of x evaluated at infinity. Well, delta of x, if anything, if x is not 0, delta of x is 0. So this term vanishes. Delta of x not equal to 0 is equal to 0. And what we're left with then is the integral of a delta function times a function, in this case df dx. So it's just going to pull out the value of df dx at x equals 0. So what we're going to get is df dx evaluated at x equals 0. That's our answer. So multiplying f of x by the derivative of the delta function pulls out the derivative of f of x at whatever the argument of the delta function is. You could just as easily have written this as x minus a, the argument of the delta function, and then it would pull out the derivative of f of x at x equals a. This notion of integrals and delta functions pulling out the value of the function gets especially interesting when you talk about delta functions and Fourier transforms. For instance, suppose we're interested in the Fourier transform of the delta function. Capital F of k now represents the k-space representation of f of x, where if this is going to be delta of x, you know how to do this integral. This is just going to be 1 over the square root of 2 pi out front times e to the minus I, k, and I've forgotten something. Instead of treating this as just the delta function at specifically x equals 0, I'm going to say x minus x naught. Do things a little bit more generally. So delta of x minus x naught here in this integral is just going to pull out the value of e to the minus ikx at x naught. So this is our Fourier transform of the delta function. It's a function of k, and x naught now is just sort of effectively a constant. In order for this to really make sense, when I take this capital F of k and substitute it back in here, you'll see we need a particular interpretation of integrals of e to the ikx. So let's go ahead and do that. Let's substitute that in. What we're going to get, 1 over square root of 2 pi out front, times another 1 over square root of 2 pi from our capital F of k. So we're just going to have a 1 over 2 pi overall. And we have an integral from minus infinity to infinity of our capital F of k over here, e to the minus I k x naught, times e to the I k x. And we're integrating now dk. So if I re-express this, 1 over 2 pi integral minus infinity to infinity, that's really ugly infinity. I've always had problems with infinities. E to the I, and then I'll write this as k x minus x naught integral dk. So this, as a function of k, x and x naught are constants in this integral since it's an integral over dk. This is just e to the I times something times k. So this is your complex number rotating around in real imaginary space in the complex plane. As k increases, you're just rotating around. So this is effectively a spiral if you want to think about it as a function of k. Depending on the value of k, you're just rotating around. And if I think about integrating a function that's spiraling around like that, the real part is going to be a cosine, the imaginary part is going to be a sine, and I'm integrating from minus infinity to infinity. So if you think about the real part as being a cosine, you're integrating a function that just oscillates. And it oscillates all the way to infinity and all the way to minus infinity. So if I say start at 0 and go to infinity, first I'll be adding up some positives, then I'll be adding up some negatives, then I'll be adding up some positive, then I'll be adding up some negative. The integral is essentially oscillating as I increase my upper limit. It's also oscillating if I decrease my lower limit. So really, you're having an integrand here, or the overall integral, depending on where you stick the endpoints, is oscillating between two values, between positive pi and negative pi, more or less. And it's not really sensible to say that that has any specific value. But keep in mind now, what we're trying to get back is delta of x. So really, the only sensible way to treat these integrals is to say that this integral is equal to 0 if x is not equal to x naught. Since that's what the value of the delta function is if x is not equal to x naught here. If x is not equal to x naught, we have this oscillating integrand, and we're saying that when the limit as x goes to positive infinity, if the upper limit goes to positive infinity and the lower limit of the integral goes to negative infinity, we end up with 0. That feels a little fishy, but if we make that definition, we get something back that resembles the delta function. If x equals x naught, of course, then the argument here is just 0. We no longer have oscillations, and our function is just constant. And the integral of a constant, the integral of 1 from minus infinity to infinity, had better be infinity if x equals x naught. So this part's okay. The 0 here is a little fishy, but if we make this definition, we get something back that looks very much like what we put in the delta function. So this is how delta functions relate to Fourier transforms, which hopefully sheds a little bit more light on what I was arguing in the lecture on free particle wave packets, being able to, really express anything. So that about sums up what I feel you guys need to understand about delta functions.
Thanks for watching. Please subscribe and don't miss out on new videos and lectures.